Okay, hey everyone. So in this mini lecture, we're looking at exponential functions and the graphs of exponential functions. So what are exponential functions? Exponential functions can look something like this, where we have f of x is equal to 2 to the x. Maybe we'll have f of x is equal to 1/2 raised to the x power, something like that. Or maybe we'll have f of x is equal to, let's say, 3 to the x power. So an exponential function is defined as a function in the form of f of x is equal to a to the x power, a to the x power. Of course, here where our a value, is greater than 0, a cannot be 1. Right? And x is a real number. So the base cannot be 1 in this definition up here, right? If you think about it, plug in 1 for a. The base cannot be 1 because we'll have 1 to the x power. That's just like the constant function, where you'll have f of x is equal to 1. 0 isn't used in the base of a, right? Because 0 to the x power is just going to be 0 for any positive x, and non-positive powers of 0 are undefined. Negative numbers can't be used as bases because an expression, if you would use, let's say, negative 6 to the x power, is not a real number, or let's say negative 4 to the x power. Let's write that out, negative 4 to the x power, right? That's not a real number if x is equal to 1/2, right? Because when the exponent is a fraction, you change it to a radical, so we'll have the square root of negative 4, so that's not a real number. So therefore, that's why a cannot be negative. So a cannot be negative, meaning it has to be greater than 0, and a cannot be 1. Exponential functions. Here we said, let's let f of x equal 2 to the x power. G of x is 1/4 raised to the 1 minus x power. And h of x is equal to negative 3 to the x power. So let's do a few examples here. Let's say we're trying to find f of 3/2. So x is 3/2. We're trying to find the function f, so we're going to use f of x is equal to 2 to the x power, right? We're going to use that one right there because of that f that we see. So f of 3/2 is equal to 2 to the, we plug in 3/2 for the x. Remember, you have to always recall that when you're dealing with a rational exponent, meaning an exponent that is a fraction, you can change it to a radical with that same base. And now you just have to remember, okay, the denominator is the index, right? The denominator is the index, and the numerator becomes the exponent. So we have the square root of 8, 2 to the third power is 8. Now we're taking the square root of 8. That's not a perfect square. So what do? Think back again, use some additional skills, break down the 8. The largest perfect square that goes into an 8 is 4, the square root of 4. Square root of 4 is 2, but that square root of 4 times square root of 2 makes the 8. So square root of 4 comes out. So here's what I was saying. 4. 4 is the largest perfect square root that goes into 8. And then that comes out once you take the square root of 4 to be 2. And then the other 2 just stays under. All right, so now we've just evaluated this exponential function. All right, so make sure you have the f of x, g of x, and h of x written down so we can refer back to them for the next couple of examples. All right, or you can just go ahead and rewind. All right, so Second example. Second example, let's go ahead and use one of the other ones. We'll use g of 3. So because it has a g, we're using function g, the x is 3, we're going to use the g of x. The g of x is equal to, what was it? 1/4 raised to the 1 minus x power. So we have g of x is equal to 1/4 raised to the 1 minus x power. Well, x is now 3. That's given, right? 3 is x. So we just go ahead and do the math. 1/4 raised to the 1 minus 3 is a minus 2 is a negative 2, right? So now you say to yourself, okay, what does that mean when we have this negative exponent? It means, okay, we're gonna flip the 1/4, right? Especially when you're taking the negative exponent of something in parentheses, or a quotient in parentheses, I should say. You just flip that. So 1/4 becomes 4/1. So it becomes 4/1, which is just 4, and it's still raised to the second power now. That's what the negative exponent did. And then we get 16. 16. So for many applications of exponential functions, we use base 10, or sometimes we use another base called e. So that e is this irrational number that's approximately 2.718 is what we use. So if you're taking an algebra course of some sort, you'll probably touch upon compound interest, and there you'll see how e is used in compound interest. So base 10 for us is called the common base, right? And then e, that's called the natural base. So let's look at graphing exponential functions. Let's graph exponential functions. So the first one I'm going to graph is f of x is equal to 2 to the x, 2 to the x. And then the next one will be f of x is equal to 3 to the x. All right, so first, all I'm going to do is just make a table of ordered pairs. And I'll have values, let's go with -2, -1, 0, 1, 2, and 3. Okay, so then we'll have f of x. F of x is 2 to the x power. And then just plug in those values of x into your function. Plug them in for x. So 2 to the -2 power, right? You have to remember properties of exponents, how if you have a negative exponent, you'll shift it to the denominator, becomes a fraction. So 1/2 to the second power makes 1/4. So I'm going to write all of these values in, but you can use some scrap paper and work them out. You're just plugging them in for x. All right, and then we get 1/2. Plugging in 0 for x, 2 to the 0, we get, 2 to the 0, we get 1. 2 to the first, we get 2. 2 to the second is 4. 2 to the third is 8. And then I'll just go ahead and plot these points. So -2 in the x and 1/4 in the y. About there somewhere. -1 and 1/2 right there. 0, 1 is right there. 1, 2 is right there. 2, 4 there, and then 3, 8 is right there. So you would just go ahead and connect the dots. Draw yourself a smooth curve, something like that. So you see as x increases, 2 to the x increases. As x increases, 2 to the x increases, right? 2 to the fourth is 16. If we were to use 5, 2 to the fifth is 32, 2 to the sixth power is 64, and so on. As x decreases, the powers of 2 are getting closer and closer to 0, but always remain positive, right? Always remain positive. So if you were to do 2 to the negative third power, you would get 1 over 8. Or if you were to do 2 to the negative fifth power, you would get 1 over 32. So it gets closer and closer to 0 as such, but remains positive. So as x decreases, the graph approaches but does not touch, right? If you look at my graph, it's kind of touching, but imagine that coming really, really close, but not touching the x-axis, right? Because the domain of the function is from negative infinity to positive infinity. Okay, so now I'm going to try this again. I'm going to go ahead and make a table of ordered pairs that satisfy g of x is equal to 3 to the x power, 3 to the x power. So I'm now plugging these values of x in to our function. So I'm just going to write down the values that I've calculated, and you can do some scrap work on your own and make sure you get the same thing. So I get 1/9, 1/3, 1, 3, 9, and then I get 27. So I'm just going to plot these points at -2 and 1/9. It's hard to show here because it's so small. And -1 and 1/3. And you see it's going through 0, 1 every time. 1, 3, 2, 9. All right, so I'm just going to connect the dots now. All right, and as you see, after drawing a smooth curve through the points that we have indicated from the table, as x increases, 3 to the x increases. As x decreases, 3 to the x gets closer and closer to 0 again, but does not reach 0, doesn't touch 0. So the graph that is shown here approaches but does not quite touch the x-axis, just like the other one. So again, the domain is from negative infinity to positive infinity, and the range going from bottom to top is from 0 to infinity, not inclusive of 0. Graph this function f of x is equal to 2 raised to the x minus 3 power, and then minus 4. All right, so if we're going to graph 2 raised to the x minus 3 power minus 4, there are going to be some transformations involved. We're going to use transformations to graph this exponential function. So let's go back and take a look at what we had previously. Here, previously, we had this. This is what we just did. This is the graph of f of x is equal to 2 to the x power. So to graph f of x is equal to 2 raised to the x minus 3 power minus 4, we're going to move that graph 2 to the x. Where do we move it? So take a look at your maybe your notes for transformations. You might have a handout or you have it in your notes. We're going to move to the right 3 units, and we're going to move down 4 units, right? So we have the minus 3 within the function, so that means move to the right 3 units, and then we have the minus 4 kind of outside of the function, so that means the original function, so the parent function, that is, so that means we move down 4 units. All right, and then you can also just calculate a few ordered pairs just for accuracy. So we have x, maybe I'll calculate 2, 3, 4, and then 5. 2, 3, 4, and 5. So what's our function? Y is equal to 2x minus 3 minus 4. So if we plug in 2 for x, go ahead and do that work on the scrap paper on the side somewhere. You should get negative 3.5. Plugging in 3 gets you negative 3. Plugging in 4 gets you negative 2. Plugging in 5 gets you 0. And go ahead and make sure you do practice that on your own time just to make sure you did do the arithmetic correctly. Using those shifts, the 3 units to the right and 4 units down, along with those um, extra ordered pairs, then we have the following graph, right? So this would be the graph of f of x is equal to 2 raised to the x minus 3 power minus 4. Now let's take a look at the function f of x is equal to 5 minus e raised to the 2 minus x power. Remember that value of e. We said it was approximately 2.718. We talked about this earlier. So let's look at some information that can help us out. So if we have the graph of y is equal to e to the x, right, that's like 2.718 raised to the x power. So we know this to be an increasing function, right, and it passes through 0, 1 as an exponential function does. If we place the negative on it, then we have to know that it's going to be a decreasing exponential function, right? So that is going to be decreasing. And then if we look at other things like the different shifts, let's go take a look at those. So before I look at the shifts, those transformations, I'm going to rewrite the equation. So I have y is equal to 5 minus e raised to the 2 minus x power, right? This is my original. Instead of f of x, I'll write y. And now I'll rewrite it as y is equal to 5 minus e. But just to help me out a little bit, I'm going to make this negative x minus 2, right? Because a negative times that x makes that negative x above, and negative times negative 2 gets us the positive 2 that we see in the original. But this is going to help me out a little bit more, so it'll make it a little bit easier for me. All right, so the graph of y is equal to e to the, here, this one right here, e to the negative quantity of x minus 2 power. So basically it's e to the negative x. E to the negative x shifted 2 units to the right. 2 units to the right. And it's because of that right there, that negative 2. All right, the next one, if we look at the graph of y is equal to negative e raised to the negative quantity of x minus 2, what is that? That's basically the graph of y is equal to e raised to the negative quantity of x minus 2. It's that reflected across the x-axis, right? It's that reflected across the x-axis. And how do we see this? We see it because of that sign in front of our function, right? So if you recall the different transformations, that sign in front of the function being negative shows you that it's reflection across the x-axis. All right, and then let's take a look at this next one. If we have the graph of y equals 5 minus e raised to the negative quantity of x minus 2. What is that? That is the graph of y is equal to negative e raised to the negative quantity of x minus 2. This is the graph of that shifted 5 units up. Shifted 5 units up, right? And how do we see that? Because of the value outside of the function. Okay, so with all of this information, we take this information and now we say to ourselves, okay, the exponential function should have an asymptote, right? As x approaches infinity, then e raised to that negative quantity of x minus 2 approaches 0. So think really deeply about that. As x approaches infinity, as x gets larger and larger and larger and larger, that whole function approaches 0. It's getting smaller and smaller and smaller. So therefore, the horizontal asymptote, I'll just abbreviate it with HA. The horizontal asymptote is y is equal to 5. Right, y is equal to 5. All right, and then maybe the next thing you want to do is just find some key points, right? Plug in some values. So let's say take some arbitrary values like x is equal to 2. When x is equal to 2, y is equal to 5 minus e to the 0 power, because remember x is equal to 2. So if you go back and look at what we have, and we look up here, 5 minus e raised to the negative quantity of x minus 2. When x is 2, you have 2 minus 2, which is 0, e to the 0 power. So then you're really saying 5 minus 1, which is 4. So when x is equal to 2, y is equal to 4. The function is equal to 4. How about, let's say when, let's do when x is equal to 1. X is equal to 1. Go ahead and plug in. Y is equal to 5. When x is equal to 1, you have 1 minus 2 is minus 1, and then a minus of a minus 1 is a positive 1. So then that's basically 5 minus e to the positive 1 power. So that's going to be approximately 5 minus e to the first power. We said it's 2.718 or 2.72. So 5 minus 2.72. I'm sorry, let's clean that up a little bit. 5 minus 2.72. So that gets us about 2.28. All right, then I'll just do one more. When x is equal to 3, y is equal to 5 minus e to the negative 1 power. Right? So when x is equal to 3, you have 3 minus 2 is 1, then you have the negative on the outside of the parentheses, so negative 1, so e to the negative 1 power. So that's going to be about 5 minus, and if you calculate that, you get about 0.37, right? That e to the negative 1 power. And then that value becomes 4.63. That's what it looks like, 4.63. If our function looks something like this, after plotting those points and understanding the different translations, the different transformations that occurred, and also looking at the asymptote, I have it in red as y is equal to 5, where it goes very close to but never quite crosses. This would be the sketch of our function. All right, and then last thing to remember, always remember in looking at exponential functions and the graphs of the exponential functions never will have a vertical asymptote. Exponential functions will never have a vertical asymptote.